let's look at an example here. Okay. I've got a rabbit run problem. The rabbit's escaping a fox. It runs 40 degrees north of west at 10 meters per second. The coordinate system is established with the positive x-axis to the east and positive y-axis north. Write the rabbit's velocity in terms of its components. All right. Let me get my notes. I've got to copy this problem over. So we'll start with our coordinate system. I'll draw that. So nothing too fancy. It says north is the positive y-axis, and then east is the positive x-axis. So our axis looks like that. Now we want to represent its velocity vector. So I'm going to treat the rabbit. All right, its center of mass is right here at the origin. And now let's draw it. It says it's 40 degrees north of west. Okay, so it's 40 degrees moving to the north side of west over here. So if I think I've got north on the y-axis, east on the positive x, south, west over here. So the vector is going to be something like that. There's my velocity vector. And the angle provided to us, that's 40 degrees. Okay. And notice I started on the west and went north. So it's north of west going up there. Now we need to get the components. We need to calculate that somehow. So what I want to do is draw my x and y components on here. Okay. So this would be my x component of the velocity, that's Vx. My y component is how far that vector stretches along the y-axis, or how far up it points. Okay, so I've got it like that. And then we also know the magnitude, right? That's at 10 meters per second. Now we're ready to calculate. So I would say Vx is equal to, now, you know, it's very tempting to say magnitude 10 meters per second times cosine theta. That's, but you got to be a little bit more careful than that. Okay. So I'll start with the magnitude. That's good, 10 meters per second. Now I want to look at how is that, what's the relation between the x and the x component and that angle that we're given. So 40 degrees north of west going up here. So notice my x component is adjacent. The angle is touching it. It starts from my x component and goes up to the hypotenuse. So I am using cosine. So I go cosine 40 degrees. But it's not it entirely yet. I have to be careful. Is it positive or negative? In this case, my x component points to the left and it's negative. Okay. So I throw that in. And I get negative 7.66 meters per second. Okay. Next, I want the y component. Okay. The y component's over here. It's going to be the magnitude, 10 meters per second. And then it's opposite my angle theta. Angle's right there. Y is over this way. So I go sine theta. And then, you know, is it positive or negative? It's positive because the y component's pointing up. All right, so plug that into your calculator and you come up with 6.43 meters per second, and it's a positive. Now what I want to do, I want to write it. Those are my components. I'm not quite done yet because I want to represent the whole vector in terms of its components and unit vectors. So V is equal to, it's going to be Vx times I hat plus Vy times J hat, or negative 7.66 meters per second I hat plus, make that plus a little bit better. And then my y component, 6.43 meters per second, and the j hat, and then I'll group it all together. I'll just add my units off to the side, meters per second. Okay. So what this tells me, because of my notation, the I hat, this is my x component, negative 7.66 meters per second, and my y component is what's multiplying j hat, 6.43, with the meters per second tagged onto it.